Hello everyone. This is the second video. Here I am explaining how to get the matrix of linear transformation or what is matrix of linear transformation. So in the first video I had given you a transformation that is t of x comma y which is equal to y comma minus x. What was this transformation? This is rotating plane by 90-degree clockwise. Okay, so this is how to represent that transformation. Matrix of linear transformation means the concept of matrices can be efficiently used to understand or to deal with all these linear transformations. Matrices act as a tool, a very important tool in linear transformation. Let us see what is the role played by matrices. See, as per this transformation I told you, this is the original system, coordinate system, standard coordinate system. See, the plane is not having built-in basis. Okay, we can choose any two linearly independent vectors as basis for a coordinate system. Okay, this is our coordinate system which we are using, that is standard coordinate system, where this vector 1 comma 0, okay, which is nothing but I cap, and 0 comma 1, this vector is j cap. Okay, these two vectors are considered as a standard basis vectors. This is our standard coordinate system. Whenever we are dealing with the coordinates, we usually use this coordinate system. Okay, here basis is 1 comma 0 and 0 comma 1. These two are linearly independent. Okay. See, in plane, in R square, any two vectors are linearly independent if they are not the multiples of each other. If those two vectors are not multiples of each other, then they always form a basis. They are linearly independent. Here we have taken I cap and j cap. These are the basis vectors, and this basis is called as standard basis, and hence this coordinate system is called as standard coordinate system. So we shall call this as our coordinate system. Okay. Now, after applying the transformation, I had shown you in the previous video how this changes. Rotate this by 90 degree, rotate the plane by 90 degree, then you will end up here with I cap here and j cap here. Correct? Now this here comes y o y dash, and here comes x o x dash. So this is the new position of I cap and j cap. Okay, so matrix of linear transformation means you have to find out where I cap and j cap lands after applying that linear transformation. Now initially the position of I cap is 1 comma 0 and 0 comma 1 at these coordinates. Now it is here 0 comma minus 1 and 1 comma 0. So you have to write it in the matrix form where I cap lands. What is the new position of I cap after applying the transformation? That is 0 comma minus 1. That is, you have to write it as a column. That particular vector where I cap lands, the new position of I cap, you have to write it in terms of a column that forms the first column of the matrix. And next j cap lands at the position 1 comma 0. Okay, this is 1 comma 0. So this is called as the matrix of linear transformation. We have written the linear transformation algebraically in terms of coordinates as a t of x comma y as y comma minus x. Even if you put here t of 1 comma 0, that gives you 0 comma minus 1. The same as this. Okay. Similarly, t of 0 comma 1 goes to 1 comma 0. J cap goes to this position. But the same thing can be represented using a matrix, and this matrix is called as a matrix of linear transformation. So if you want to check where 1 comma 2 goes to, either you can put it in this transformation, or else you can directly multiply the vector 1 comma 2 with this matrix. See, for example, Look here, t of 1 comma 2. This is one random vector. 1 here, 1 comma 2 comes here, somewhere over here. This is 1 comma 2. T of 1 comma 2. After applying the transformation, what is its new position? 2 comma minus 1 as per the definition of this transformation. Now, the same can be obtained using the matrix. Instead of writing this, I will multiply the vector, that is 1 comma 2. Okay, this vector has to be multiplied with this matrix to the left. Then what you will get? This gives you 0, 1 is 0, 1, 2 is 2, then minus 1. See, same vector you got. Here also it is going to 2 comma minus 1. In this case also going to 2 comma minus 1. So instead of referring to the transformation in the algebraic form, I can use this matrix of transformation and I can get where the vector lands just by multiplying that vector by this matrix of the transformation. So that is called as matrix of linear transformation. Whenever we are using standard basis, matrix of linear transformation is nothing but where the standard basis vectors I cap and j cap land after applying the transformation. The new position of I cap and j cap must be written in terms of columns, and so this acts as a substitute for this linear transform. Instead of referring to the linear transformation every time, now this is a representative of the linear transformation in terms of a matrix. So every matrix you can view it as a linear transformation. Under the chapter linear transformation, whatever the linear matrix is given to you, you can view it as a I cap j cap, new position of I cap and new position of j cap when it is given with respect to the standard basis. Now let us consider a new basis 1, 2 and 2, 1. These two vectors also form a basis because they are not multiples of each other. So they span the whole space R square, basis of R square. So whatever I am giving example here, all are related to the vector space R square over R. So we had the standard coordinate system where we were checking where I cap and j cap lands after applying the transformation. This is standard coordinate system. Here we are using the standard basis. We call it as our coordinate system. So because we are using this coordinate system most of the time, standard coordinate system. Now I have given you a new basis s equal to 1, 2, 2, 1. This basis I have named in terms of our coordinates only. 1, 2 and 2, 1. These are our coordinates. As per our coordinate system, where comes 1, 2? 1 here, 2 here means this is one vector 1, 2, and I need 2, 1, that is here. 2, 1. These two vectors are not in the same direction, so they form a basis, and you know that any vector in a plane is a linear combination of basis element, or it is scaling and adding the basis element. Now for example, consider your standard basis. This is I cap and j cap, correct? Now if you want to go to the point 3, 1, 1, 2, 3, 1, 2, 3 and so on. This is y-axis. Now 3, 1 means what? It is 3 times 1, 0 plus 1 times 0, 1 gives you the value 3, 1. Means you have to scale I cap, increase its length by 3. Okay, 3 times I cap and 1 time. Keep the length as it is, 1 time j cap. Now add these two vectors. See, these are free vectors. Here when you have these vectors, you can't add. Means you have to bring it to here, head to tail. Correct? No. So here comes, this is 1 times j cap. Now as per the triangular law of addition, this point is nothing but 3, 1. So 3, 1 is a linear combination of 3 I cap and 1 into j cap. So any vector for that matter, it is a linear combination of basis vector or scaling and adding basis vector. So now when you take 1, 2 and 2, 1 as a new basis, every vector in R square or every vector in plane is a linear combination of these two basis vectors. So it forms a new coordinate system. Now with respect to this basis, there is a new coordinate system, that is called This is a new coordinate system with 1, comma 2 and 2, comma 1. These are bases. Now these two vectors play the role of I cap and j cap. Therefore, so there is one coordinate system, that is our coordinate system. This is new coordinate system. Now the matrix of linear transformation will definitely change with respect to this basis. With respect to the standard basis, that is where I cap and j cap lands after applying the transformation. But now the role of I cap is played by this 1, comma 2, and the role of j cap is played by the vector 2, comma 1. These two vectors are now in our language. It is like there are two different languages. So what they mean is same, but the way they say is different. That is in this language and this is another language. So that is how to understand it. So now I have to get the matrix of linear transformation with respect to this basis. So where these two vector land after applying the transformation, that I have to find out. See, to know that, first let us find out where 1, comma 2 will go to after applying the transformation. What is my transformation? It is rotation by 90-degree clockwise. It is represented like this. T of x, comma y equal to y, comma minus x. Therefore, t of 1, comma 2 will go to 2, comma minus 1. And t of 2, comma 1 will go to 1, comma minus 2. Correct? Now, all these vectors are in our language because I have taken 1, comma 2 and 2, comma 1 in my language. That is our standard coordinate system. But I need the representation of these vectors in the new coordinate system where these two vectors acts as a basis vectors. So any vector, I have to write this as a linear combination of 1, comma 2 and 2, comma 1. Okay, so I have to get what 2, comma minus 1 in the new coordinate system is called. Okay, for that I will take any vector a, comma b. Write it as a linear combination of x into 1, comma 2 plus y into 2, comma 1. Okay, linear combination of these two vectors means I have to scale these vectors and add them to go to the required position. So I don't know any general vector a, comma b in R square is written as a linear combination of these two vectors because these two are considered as bases now. So let us solve this system. You'll get x plus 2y equal to a, and you'll get 2x plus y equal to b. You can do it individually. Here x into 1, comma 2 plus y into 2, comma 1, then p into 1, comma 2 plus 2, q into 2, comma 1, getting the constants in every case. But you find it for a general vector. That will help you to write for all other vectors. So any vector of a, comma b, when it is written as a linear combination of 1, comma 2 and 2, comma 1, how it looks like in the new system. Let us find out that. So let us solve this. So multiply this equation by 2, 2x plus 4y equal to 2a, and here in this case 2x plus y equal to b. So now subtract these equations. You will get 3y equal to 2a minus b plus int minus. So y equal to 2a minus b by 3. This is how coordinate of y looks in the new coordinate system. Similarly, I need to get x now. So to find x, substitute in any of the equation. So I will write here x equal to a minus 2y, which is a minus 2 into 2a minus b by 3. Okay, so this is equal to 3a minus 4a plus 2b by 3, which is equal to 2b minus a by 3. This is how x looks like in the new coordinate system. Therefore, any vector a, comma b in our standard coordinate system will go to the vector 2b minus a by 3 and 2a minus b by 3 in the new coordinate system where 1, comma 2 and 2, comma 1 acts as a basis. See, there is no built-in or intrinsic basis for a plane. Whatever basis vectors we choose, based on that, every other vector can be reached as a linear combination of those two vectors. correct? No. So in case of a standard coordinate system, it is scaling I cap and j cap and adding to reach to the new position. Now in this new coordinate system, scaling these two vectors and adding to reach the required position, in that case its coordinate representation changes because it is in terms of 1 2 and 2 1, not in terms of 1 0 and 0 1. So any vector a comma b of r square, which is in our language, can be written like, here I will write now. Therefore, see here, any vector a comma b, this is in our system, our standard system, our system is represented in new system, new coordinate system as 2b minus a by 3 and 2a minus b by 3. Therefore, 2 comma minus 1, as per our system, 1 comma 2 goes to 2 comma minus 1, correct? Now, but in this new system where 2 comma minus 1 goes, this is a, this is b. Apply this formula. 2 into b, minus 2 minus 2, that is minus 4 by 3. This goes to minus 4 by 3 and comma. Similarly here 2a minus b. So 2a, 2 2 is a 4, minus of minus plus 5 by 3. Okay. This is equal to, again here apply where 1 comma minus 2 goes to in our new system. Apply this. 2 2 is a minus 4 minus 1 minus 5 by 3 comma, then 2 plus 2 4 by 3. So these are the positions. This is how we say the same vectors in the new coordinate system. So it is nothing but here saying it is nothing but minus 4 by 3 times 1 comma 2 plus 5 by 3 times 2 comma 1 will give you the vector, the required position of the vector. After applying the transformation, it goes to 2 comma minus 1. 2 comma minus 1 in this new coordinate system, it is written as minus 4 by 3 comma 5 by 3. That is because, see, it is minus 4 by 3 times 1 comma 2. 1 comma 2 is here. Minus 4 by 3 means in the negative direction. You have to scale this vector in the opposite direction by the some factor around minus 1 point some value. You will get around like this. Okay. This is the small vector. Then so next is 5 by 3 times 2 comma 1. It is not in the opposite direction. 5 by 3 means 1 point some value. Squish this vector, reduce its length, and around 1 into some 2 comma 1 means around like this. Becomes short. This gets elongated but in the opposite direction. Now add these two vectors probably here. So when you add these two vectors, this is the position 2 comma minus 1. Okay, 2 comma minus 1 is in our language. 1 comma 2 goes to 2 comma minus 1. But we have to write how the scaling happens in terms of these two vectors. It is minus 4 by 3 times 1 comma 2 plus 5 by 3 times 2 comma 1. If you do it like this, then you will go to the vector 2 comma minus 1. That is the position in terms of these basis vectors. Therefore, matrix of T with respect to the basis S is given as A equal to, you have to write now these vectors minus 4 by 3, 5 by 3 in terms of columns, and minus 5 by 3 and 4 by 3. Okay. 1 comma 2 and 2 comma 1 now acts as the basis. Okay, that acts as I cap and j cap. Where I cap lands, you can't directly write 2 minus 1 and 1 minus 2. If you write matrix of the transformation with respect to this standard basis as 2 minus 1, 1 minus 2, this is wrong. This is in our coordinate system, we call them as 2 minus 1. But in the new basis, new coordinate system, where these basis vectors will go to, that you have to find out in that language. It is little complicated though, but if you understand what exactly happening here, then it is easy to remember. So when you have the basis different, basis other than the standard basis, so in that case you have to find out where these vectors land in terms of the given basis. So this acts as 1 comma 0 now, and this acts as 0 comma 1 in the new system. So where I cap lands, it lands at the point 2 comma minus 1, but 2 comma minus 1 don't write directly. 2 comma minus 1 in the new language is called like this. Okay, that vectors you have to write. So when you are finding matrix of linear transformation with respect to a basis other than the standard basis, first apply the vectors where they will go to. Once you get those vectors, then convert it into these vectors in terms of these vectors. Means you have to write them as a linear combination of 1 comma 2 and 2 comma 1. That gives you the matrix of the transformation. Now when you apply any vector, when you multiply any vector by this matrix, then you will get where it goes in the new coordinate system. So now when you want to check under this basis where the vector 1 comma 0, 1 comma 0 is nothing but 1 comma 2, where 1 comma 2 goes to minus 4 by 3 comma 5 by 3. Now when you apply the matrix of transformation to that vector, you have to get this answer. Let us see. Is it was minus 4 by 3 and this gives you 5 by 3. Look, it is same as this. Okay, because 1 comma 2 in the new coordinate system, it acts like a I cap. It is called as 1 0. In the new coordinate system, 1 comma 2 is called as 1 comma 0. Therefore that 1 comma 0 goes to minus 4 by 3 comma 5 by 3. That is what we got here. T of 1 comma 2 is going to this vector, but this vector is called like this in the new coordinate system. Okay, because 1 comma 2 in terms of new coordinates, it is 1 times 1 comma 2 plus 0 times 2 comma 1. If you want to go to this vector, therefore coordinates of 1 comma 2 are 1 comma 0 in the new coordinate system. Intuitive idea about any concept is very much essential, because here basis vector, that role is played by 1 2 and 2 1. Similarly, you have an infinite number of bases for a given space R square. So therefore there are infinite languages you have to communicate between your standard coordinate system and those new coordinate systems. So there you will get the matrix of change of basis. That I will explain in the next video, how to get the matrix of change of basis. That helps you to communicate between different systems where the standard basis and some other basis are chosen, or two different bases are chosen based on that. Therefore 1 comma 2 in the new coordinate system, it is nothing but 1 times 1 comma 2 plus 0 times 2 comma 1. Then you will get that vector. Therefore 1 comma 2 is called as 1 comma 0 in the new coordinate system. These are called as coordinates. These are coordinates of the vector. 1 comma 2 anyway we are writing in our language. In the new language it is 1 0. Therefore 2 comma 1 is nothing but 0 times 1 comma 2 plus 1 times 2 comma 1. That becomes 0 1 in the new coordinate system. So this is how to get the matrix of linear transformation. Therefore, matrix of linear transformation with respect to standard basis, they are not standard basis is nothing but where I cap and j cap land after applying the transformation. After applying transformation. Okay, you have seen it there. So the transformation was t of x comma y equal to y comma minus x. Now the same transformation is represented as the matrix 0 minus 1 and 1 0. Means I cap goes to the new position 0 minus 1 and j cap goes to the new position 1 0. With respect to standard basis, it is easy. But when you have other basis, means other than the standard basis, so in that case, first you have to calculate where these new basis vector will go as per our transformation, because our transformation, whatever transformation you write it algebraically, it will be in terms of standard coordinate system only. So first you find out where these new basis vectors will go after applying the transformation. That will be in our language only. Convert it into the basis language, its new coordinate system. So you have to write that vector in terms of these basis vectors, then find the coordinates. Coordinates are nothing but how it is called in the new coordinate system. See, y comma minus x, you have to write this as, suppose a, b and c, d, these are the basis vectors. So p into a comma b plus q into c comma d. Get these pq are nothing but coordinates of the vector y comma minus x in the new coordinate system. Okay, after getting that only, write it in terms of columns of the matrix. That gives you the matrix of basis, matrix of linear transformation with respect to the basis. Yes, that is how to find out. I hope you understood the concept. If you like my videos, please share and subscribe to my channel. Let us see what is matrix of change of basis to communicate between two systems, two coordinate systems in the next video. Thank you for watching.